Hello everyone, welcome back. So, this is the lecture 5 in week 3. Today, let us first consider one more example and then we will derive the differential equation of equilibrium. So, our example today is the 3D stress field is given and it is 6, 3, 2, then 1, 2, 1. Our task is to find out the 3 principal components. So, find sigma 1, sigma 2, sigma 3. That is the first task. Then plot Mohr circle. Right. So, let us solve this example. Now, we already know this is a symmetric matrix. So, we have the 3D stress field given. Now, what was the characteristic equation that we derived? Sigma cube minus I1 sigma square plus I2 minus I3 is equal to 0. So, our task is to find out I1, which is the sum of the leading diagonal. So, 6 plus 3 plus 2, and that is 11, right. So, I1 is 11, I2 we have to figure out. So, let us consider sigma xx, sigma yy and tau xy. So, it is 18 minus 1 plus then sigma xx, sigma zz and then tau xz. So, it will be 12 minus 4 and then the last one sigma yy, sigma zz and tau yz. So, that will be 6 minus 1. Okay. So, if you solve this, you will get I2 as 30, right. And then I3, which is the determinant of this matrix, that we can figure out. The first element is 6 and then that multiplied by 3 into 2. So, 6 minus 1, then minus 1 times will have 2 minus 2, then plus 2 times we have 1 minus 6. And again, if you simplify this, I3 is 20. So, the characteristic equation we get is sigma cube minus I1, which is 11. So, 11 sigma square plus I2, which is 30 in our case. There will be I2 times sigma, which I missed. So, 30 sigma minus 20 is equal to 0. Now, we can simplify this equation. So, we do that. Sigma cube minus sigma square, then minus 10 sigma square, because we take 1 sigma square here, plus 30 sigma minus 20 is equal to 0. If we take sigma square common, we have sigma minus 1, then minus 10 sigma square. Then if we take minus common, so the second term will have minus. So, minus 10 sigma minus 20 sigma plus 20 is equal to 0. So, we have sigma square times sigma minus 1, then minus here we have 10 sigma, then within bracket sigma minus 1 minus if we take 20 common, sigma minus 1, which is equal to 0. So, we have sigma square times sigma minus 1, then here we have sigma minus 1 times 10 sigma minus 20, which is equal to 0. So, we get the first root sigma minus 1, within bracket we have sigma square minus 10 sigma plus 20 is equal to 0. So, the first root we have here sigma is equal to 1. The remaining two roots we can solve this quadratic equation. So, for the remaining two roots we have sigma square minus 10 sigma plus 20 equal to 0. So, we have sigma is equal to minus b. So, it will be plus 10 plus minus square root of b square minus 4a is 1 times c, which is 20, divided by 2 times 1. And if you solve this expression, you will get two roots, which will be 2.76 and 7.24. So, our principal components are sigma 1 is 7.24, sigma 2 2.76 and sigma 3 is 1. Now, using each of them, we can find out the direction cosines corresponding to each principal stresses, and I leave that as an exercise. So, the direction cosines or eigenvector corresponding to each values of sigma that we get is minus 0.3015, minus 0.3015 and then 0.9045. That is the first eigenvector. Each component will give us the direction cosine. So, we have nx, ny and nz. So, nx, ny and nz. The second eigenvector is 0.3868, 0.9058 and then 0.1730, and the final and last eigenvector is minus 0.8715, minus 0.2977 and then the last one is minus 0.3897. So, this I leave it as a home task. I have already explained how to solve this. So, use first value of the principal stress in the original eigenvector equation and use the property of direction cosines, you will get this value. Okay, so, we will draw the Mohr circle in a minute, but before that let us cross verify whether this stress invariance, that is I1, I2, I3, they are truly invariant in terms of sigma 1, sigma 2, sigma 3. So, let us cross verify. So, we know I1 is equal to sigma 1 plus sigma 2 plus sigma 3, and the sum of this, if you do, you will again get 11. So, that is the first invariant. Similarly, what we can do, I2 is equal to sigma 1 times sigma 2 plus sigma 2 times sigma 3 plus sigma 3 times sigma 1, and that will be 7.24 times 2.76 plus 2.76 times 1 plus 1 times 7.24. And if you solve this, you will get 29.98. It is almost equal to 30, because we consider up to 2 decimal place here. That is why we have some numerical error due to truncation, and otherwise this value is very close to 30. Okay. So, the second invariant also matches. So, the last one I3, which is equal to sigma 1 times sigma 2 times sigma 3. So, we have 7.24 times 2.76 times 1, and if you find out this expression, we have 19.98. Again, because of truncation, we have small error here, but otherwise it is very close to 20. So, we also cross verify the stress invariance once we get the principal stresses, right. Now, our next task is to find out the solution in terms of the principal stress in pi plane. So, this is our pi plane. Actually, it is here within that circle. So, pi plane, and here you can see the small code given, which is used to draw this Mohr circle. So, we have along x axis we have sigma, and along y axis we have tau. What we do, we have our sigma 3 is 1, sigma 2 is 2.76, and sigma 1 is equal to 7.24. So, we can mark it here. So, this is the point where we have sigma 3, then here we have sigma 2, and here we have sigma 1. So, due to aspect ratio it looks like ellipse, but otherwise it is actually circle. You can try this code using MATLAB. So, what you can see here, they are the 3 principal stresses, and then first what we do, we find out the radius which is here, and before that first we find out the center point. So, this is the center. So, if you consider say sigma 1 and sigma 3, obviously if we take the average, somewhere here will be the center, right. And then from this point, if we find out the difference with sigma 1, so this is our R1. So, that is what is evaluated here. Obviously, the y coordinate is 0. So, we know the center point of the circle, and we also know the radius. Then using this function file here, we plot the circle, and then we repeat the same exercise for other 2 circles, right, and that is how we get this Mohr circle in 3D. Now, obviously, we can easily locate the maximum shear stress, and we can also identify the respective normal stress, right. Now, the question is, if we consider any point inside this, say this point, right. For this point, we have x and y coordinate. So, we can see our x coordinate is 3 and y coordinate is 2, right. So, at this point, we have sigma n is 3, that is the normal stress, and shear stress tau n is 2. Now, once we find this point in the pi plane, then we can find out nx, ny, nz, that is the orientation of that plane. If you recall, what is the expression of nx? In the last class we discussed. So, that is nx square is sigma n minus sigma 2 times sigma n minus sigma 3 plus tau n square divided by sigma 1 minus sigma 3 times sigma 1 minus sigma 2. So, if you put the values of sigma n, sigma 1, sigma 2, sigma 3 and tau n, we can easily find out this nx, and similarly we can also find out ny and nz. So, this again I leave it as a home task for you. You just put the values of sigma n, tau n, which is 3 and 2 in this case, and then we have sigma 1, sigma 2, sigma 3. So, that clearly explains how to start with the 3D stress field and then find out the principal stresses and then draw the Mohr circle. Then if you consider any point within that Mohr circle, say this one, we can easily find out the respective plane on which this stress sigma n and tau n they are acting. Okay. In your practice problems, you will have similar problems that you try, and then if you have any difficulty, let us know. Okay. So, let us continue further. Now, if we have a 3D stress field, we have learned how to find out the stress components acting on a particular plane. Let us revisit the problem once more, and what we will do today is the derivation of differential equation of equilibrium. Let us first consider the 3D stress field, and then I will explain how to get this differential equation of equilibrium. So, let us consider a differential element again. And for the time being, let us consider all the stress components acting along x, right. So, we have normal stress. So, here we have sigma xx, and the differential element has the sides delta x, delta y, and then delta z. You can draw all the components of stresses acting on this differential element, and obviously under the action of those components, the system will be in equilibrium. So, for that, how to derive? We will consider the variation of this normal stress over a length of delta x. So, we have on the left face, we have the normal stress sigma xx. Obviously, on the right face, we have sigma xx plus delta sigma xx. That is the variation over this normal stress of sigma xx. What is our objective? Again I repeat, we will derive the equation of equilibrium. you have learned equation of equilibrium in your engineering mechanics. So, let us try that for this problem. How many directions we have? We have 3 directions x, y, z. So, we will have 3 different equations of equilibrium along x, y, z. So, first one we will derive for the x, and then obviously similar procedure will follow for y and z. Now, for the x direction, so this is the normal stress. What are the stresses acting? If you recall, so we have a component here and another component acting on this face. So, this is tau y of x. Obviously, this will be tau y of x plus delta tau y of x, right. And then we have z face along which we will have components acting along x direction. So, let us identify that. So, we have here, and then on this positive face we have the component. So, the one on the far end, it is tau zx, and at this end we have tau zx plus delta tau zx, right. So, we have identified all the stress components acting along x direction. I am not drawing all other components because then it will be difficult to identify. However, you can populate all the faces with the remaining stress components, right, that we have already discussed. So, what we will do now is we will apply the equation of equilibrium along x. So, we will identify all the forces acting along x direction and then sum them up and equate it to 0, right. Okay. So, the first component is we have on the positive face. So, we have here sigma xx plus delta sigma xx. It is acting over a face of delta y times delta z. So, that is the total force, minus we have sigma xx over the opposite face, and then that is multiplied by delta y times delta z. Then we have tau yx plus delta tau yx acting over an area of delta x times delta z, minus the opposite face we have tau yx, area remains same. So, it is delta x times delta z. Then we have tau zx plus delta tau zx times the area, which is delta x delta y, and over the opposite face we have tau zx times the same area delta x delta y. Then we also have the body force. So, the volume is delta x delta y delta z. Then we have the material density times the gravitational acceleration along x. Now, here you have to keep in mind that x, y, z plane can be oriented in space. So, we can have the component of gravitational acceleration acting along x, y, z. Although normally we consider z axis vertical, but that is not the case here. Now, obviously, some of the components will get cancelled, so that we will do in a minute. But before that, let us just write down the variation delta sigma xx. It is nothing but if we differentiate sigma xx with respect to x and then find the variation over the length delta x, we get basically the variation delta sigma xx. Similarly, delta tau yx is equal to tau yx over the length of delta y, and then delta tau zx is equal to differential of tau zx with respect to z times the length over which we consider the variation. So, this is delta z. Okay. And one more issue, normally this body force is very small because this differential volume delta v is very small. So, we can actually neglect this component if we consider very small volume. Otherwise, if it is a finite volume, we can also add this. Now, you can identify, if we open the bracket, obviously this will get cancelled. Similarly, this one will get cancelled, and then finally, for the last components of stresses acting along z plane, we will have these two components cancelled, right. Okay. So, we have delta sigma xx times delta y delta z plus delta tau yx times delta x delta z plus delta tau zx times delta x times delta y, which is equal to 0. Let us consider this volume delta v is very close to 0, and then we can neglect the body force. Now, if we put the expression of delta sigma xx, delta tau yx and delta tau zx, what we get is differential of sigma xx with respect to x times we have delta x, delta y, delta z plus, for the second term, we have differential of tau yx with respect to y, then we have delta x, delta y, delta z, and the last component we have differential of tau zx with respect to z, and then again delta x, delta y, delta z is equal to 0. Obviously, this factor delta v is common, so we can take it out, and then our differential equation of equilibrium is so that is the first differential equation of equilibrium. Obviously, we do not consider the body force. If we have body force, one more term will come on the left hand side. So, that is the first differential equation of equilibrium along x direction, right. Now, if you repeat the same exercise along y and along z, we will get two more equations, and that we can easily derive just by looking at this expression in equation 1. So, the second equation of equilibrium is tau, we have xy delta x plus sigma y plus tau yz is equal to 0. That is the second equation, and the last equation so, we have 3 equations of equilibrium. Okay. So, the first equation from equilibrium along x, second along y, and the third along z. Right. So, that completes the exercise. So, we have 3 equations of equilibrium for the stress field whose dimensions are delta x, delta y, delta z. Okay. So, let us conclude here. We will continue with few more examples on this topic, and then we will also discuss octahedral stress and other components of a 3D stress field in our next class. So, go through this derivation and obviously complete the home task that is given to you. Try the equilibrium along the remaining 2 directions and see whether you get this same set of equations that is derived. Okay. Thank you very much.